Question 1. Potassium iodide is used as a reagent in both inorganic and organic chemistry. A. Ki form an ionic lattice that is soluble in water. Part 1. Define enthalpy change of solution. Okay, so first we need to put 1 mole of ionic solid in water and dissolve it. And it must dissolve in a sufficient amount of water, and therefore it will form an infinite dilute solution. Okay, we need to make sure all the solids dissolved, then the energies that release or absorb, it can be measured. Okay, for part 2, Ki has a high solubility in water, although its enthalpy change of solution is endothermic. Explain how this high solubility is possible. Okay, so first you must have idea or understanding about enthalpy change of solution. When this enthalpy change of solution is more exo, is more soluble. However, in this question, is telling us that it's endothermic. Means theoretically is less likely to dissolve in water, but it still has a high solubility. We can use the entropy and the Gibbs energies to explain this one, because the Gibbs energy is the one that telling us whether the reaction is spontaneous or not. When it's negative, means it's spontaneous. Okay, so first, you need to know the movement of the particles of Ki. When the potassium iodide in solid form, all the ions in a fixed position. Once it's dissolved, these ions, they are freely moved. So when they have more weight to move on, the entropy will increase. So means the delta S is going to be positive for sure. So when the entropy increases, so what is the effects on this solubility? So first you need to use the Gibbs equation to explain. So delta G equal to delta H minus T delta S. And after that, you need to use the entropies that we discussed just now. Okay, so first you need to put this item, means the T delta S. T is the temperature. So when this potassium iodide dissolve in water, the T delta S become larger. Again, so when the solid dissolve, there is a large increase in entropy, which will make the T delta S larger. Okay, when the T delta S is larger, it's going to overweight the delta H, because delta H is minus a larger amount here, and eventually the delta G is negative. So means the high solubility is depends on the entropies here. When entropy is high, then the delta G is negative. B. Table 1.1 give some data about halides, the chloride bromide iodide, and their potassium salt. So in this part, there is enthalpy change of hydration and the lattice energy of potassium halide. Okay, later we will check on these values, see what is asking. Part 1. Explain the trend in the enthalpy change of hydration of halides ion. So now we just look at the hydration of halides. So from chloride to iodide, so it's negative 364 to negative 293. It's become less exo, decreases. So why it become less exo when down the group? So we can use the size to explain. When down the group, the size of this halogen is getting larger. So before that, you need to know the attractions that produce. So the enthalpy change of hydration is because of these gaseous ion dissolve in water. So when the, let's say, gaseous chloride, gaseous bromide, gaseous iodide dissolved in water, so it will form bondings with water. The attractions that produce is ion dipole forces. Ion means the anion, dipole means is from the water. So means the attractions that form between the chloride and water is stronger. Why? Because the size of chloride is smaller and it can release more energy when dissolved in water. And the iodide, because the size is larger, attractions is weaker with water, so the ion dipole forces that form is weaker. So we know that the ion dipole forces is weaker, okay, when it's down the group. Therefore, it will release less energy and the hydration enthalpy is less negative. That's the things that you must know. Okay, so this is answer, right? So ionic radius is larger, or you can say the ionic charge density decreases down the group. Charge density means depends on the charge and volume. Because charge is -1 for all, size of this chloride is smaller, so the charge density is greater. So attraction with the water is stronger. Okay, part 2. The delta H solution of these potassium halides are almost constant, almost the same. Use the hydration enthalpy and lattice energy in the table 1.1 suggests why. Okay, so first you need to recall the equation. Delta X solution equal to delta X hydration minus the lattice energy. Okay, so we will use these values. Okay, so because here only show the enthalpy change of hydrations for the halides, no potassium, but it's actually very similar because they are all potassium salt. So when down the group or when from this chloride to bromide, so we know that the change is 29, so it's plus 29, and the lattice energy is plus 31. They are quite close, means the difference between the halides here, the enthalpy change of hydration and the lattice energy is quite close, the change. And from bromide to iodide, the change is also very close, so it's plus 42 and plus 41. We use these values to see. Okay, let's say now we have the values for this hydration enthalpy. Let's say it's X. Lattice energy, let's say is Y. For the hydration enthalpy, the change just now is 42 from bromide to iodide. So it's, let's say, positive 42. So it's minus this, sorry, it's not positive, it's plus. Okay, so it's the difference is 42, 42. And this one is 41, the difference. So because X, okay, with 42 plus 42 and Y plus 41, so eventually the difference is very close. So that's the reason why, okay, we have this answer here. The difference between this lattice energy and this hydration enthalpy remains roughly constant. Because the difference is constant, means the difference between here from these halides. So therefore, the solutions, this delta X solution is almost constant. Part 3. The enthalpy change of solution of the Ki is positive 221 kilojoule per mole. Use this information and the data in table 1.1. Calculates the enthalpy change of hydration for potassium ion. Okay, again, you need to use this equation, the enthalpy change of solution and enthalpy change of hydration minus the lattice energy. Solutions already given. Hydration enthalpies for these potassium ion you need to calculate. Here, this one we can get from the table. This hydration enthalpy for the iodide here, negative 293, and substitute to this equation, okay, minus the lattice energy. Lattice energy, again, use the values here, negative 629. So calculate, you get a negative 315. Of course, you need to get a negative value because the gaseous ions dissolve in water, right? And is always XO. Okay, part 4. Solid this lead iodide form when the Ki is mixed with this lead-2 ion aqueous solution. The solubility products KSP for this lead iodide is 7.1 times 10 power negative 9. Calculate the solubilities of this salt. Okay, so first you must have the idea something like this. This lead iodide, if you partially dissolves and form these ions, these cations and anion. Let's say X mole of this salt is dissolved, and it will produce X mole of the lead-2 ion and 2 X mole of the iodide. So this is ideas that you must have. Means the X here, it can represent the solubilities of the salt. So because it's all from the salt here, right? Is dissolved and form these 2 ion. If you can calculate X, means you can get the solubility. So first, you need to get this KSP. So KSP equal to the concentration of the lead-2 ion times the concentration of iodide square. Okay, because the coefficient here is 2, right? So you must put square here. Then you substitute the X and 2X into this expression. So this one is already given, KSP equal to the X times 2X squared, means eventually you get 4X cubed. So X eventually will be 1.2 times 10 power negative 3, right? So this is solubilities of the lead-2 or lead iodide. Part 5. The ionic radius of the lead-2 ion is 0.12 nanometer compared to 0.133 nanometer for potassium ion. So means it's smaller. Suggests how the lattice energy of the lead-2 iodide differ from this potassium iodide. So because size is smaller, so when these lead-2 ions form bonding with this iodide, so it's going to be stronger because it's smaller. So what we expect is the lattice energy of lead-2 iodide is more exothermic because a stronger attractions form between the lead-2 ions and the iodide, right? So it just because it's smaller and it has a greater charge, okay, and smaller radius. So the lead-2 ion has a greater charge because it's 2 positive. Here this one is positive and is smaller in size. So the attractions between the lead-2 ion and iodide is therefore stronger. Part C. Ki slowly iodizes in air, forming this iodine. So we have this reaction 1 showing the formations of iodine. Enthalpy is given negative 203.4 kilojoule per mole. Okay, so we're going to use the standard entropy here. Standard entropy is not the delta S. Delta S, it can be negative, positive. Standard entropy is always positive, right? Because it's the molar entropy with the substance. Okay, let's see what they're asking. Part 1, calculate the standard entropy change for reaction 1. Reaction 1, you need to consider all the reactants and products. Okay, products is here, reactants here. So you need to use the molar entropy of the products minus the molar entropies of the reactant, okay, which is something like this. So the sum of the molar entropy of the products minus the sum of molar entropy of reactant. The products, again, they are these potassium carbonate and iodine. So you need to find the values from the table. 155.5 and the iodine is 116.1. So remember to put the to consider the coefficient here because it's 2 here. Here need to times 2 for both. Okay, minus the reactant again is Ki CO2O2, so you get the values from here, Ki O2, oh sorry, CO2 and O2. Again, remember the coefficient 4 to 1, 4 to 1, right? Here, 4 to 1. So eventually, the delta S, you should get negative 514.5 for us, negative 514.4. Okay, this one is quite consistent with the equation. Why? Because the delta S now is negative, so means become less random. So from the equation we can predict actually. So it's actually from gas to form, see, solid. So means become less random. So from a more random to less random means the entropy decreases. Part 2. Use your answer in C part 1 shows that the reaction 1 is spontaneous at 298 Kelvin. Again, you must use the Gibbs equation. Delta G equal to delta H minus T delta S. Okay, so you just substitute the values given. It's already here. And enthalpy is this. Entropy, you use the one that you obtained just now. So negative 203.4 minus 298, okay, T, delta S. This part you need to convert the entropy in joule to kilojoule, joule per Kelvin per mole. So you need to use this 514.4 over 1000, convert the joule to kilojoule, right? So eventually you get negative 50.1 kilojoule per mole. Okay, part 3. The group 1 carbonates are much more thermally stable than group 2. Okay, state and explain the trend in the thermal stability of group 2 carbonates, group 2 carbonates. Because it's asking state, okay, you must say down the group the thermal stability increases or decreases. After that, explain. Only 2 marks. Okay, so down the group, everyone should know that the thermal stability increases means it hard to decompose. So why is hard to decompose? Because of these effects, the polarization. So we know that when down the group, the ionic radius increases, means from magnesium to calcium to strontium to barium ions, the size is getting larger. So means the metal cation size is getting larger, and the charge density is decreases. Means is polarizing power is weaker, is less likely to distort the carbonate. Okay, carbonate has quite a numbers of electrons. For the magnesium, because magnesium is smallest in size, so the charge density is greatest, it can distort or it can polarize the carbonate, means it can attract the electrons toward itself, and eventually it can weaken the CO bond, and you can form magnesium oxide and CO2. So therefore, we know that when down the group, the cationic size is larger, the polarization of the carbonate is lesser. So there will be a less polarization of ion, means the carbonate, and the CO bond is less weakened down the group. Less weakened means it's harder to break. So means it is harder to form the metal oxide and CO2. Okay, part D. A student electrolyzed a solution of the Ki for 8 minutes using a direct current. Okay, half equation is given for this anode. So iodide oxidized to iodine, release 2 moles of electron. Okay, part 1. Write a half equation for the reaction occur at the cathode. Okay, because it's the Ki solution. So in the solutions, there are potassium ion and the hydrogen ion. Okay, of course, hydrogen ion, it will be the one that choose, because this one, the electropotential is more positive. So it will gains more likely to gain electron compared to potassium's this ion. So means in this half equation, including symbols, so you need to use the hydrogen ion. Okay, hydrogen ion, okay, equals plus 2 electrons to form the hydrogen gas. So eventually it will discharge to gain the electron. Okay, this is a calculation part. Part 2. After the electrolysis, the iodines produce required 21.35 cm cube of 0.1 mole per dm cube sodium thiosulfate to react completely. Okay, so this is the equation. We just need to know the mole ratio is 1:2 ratio. Calculate the average current used in the 8 minutes during the electrolysis. So first, of course, we need to use the volume and concentration of thiosulfate here to calculate the moles of thiosulfate. So mv over 1000, so you can get the moles of the thiosulfate, which is 2.135 times 10^-3. So because the mole ratio is 1:2, so the moles of iodines therefore is halved. So it's 1.0675 times 10^-3. Okay, so this is the moles of iodines that are produced. Okay, and we know from the titration. Yeah. Okay, so now let's calculate further. So we need to know the charge that used. So the charge that used, we need to use the moles of electron. Okay, so this one we need to use the moles that we calculate just now times 2. So from here we already know, yeah. So it's involved 2 moles of electron, right, to produce this 1 mole of means when 1 mole of iodines produced, so we release 2 moles of electron. Okay, so here need to times 2. Then we need to times the Faraday constant. Faraday constant is 96500 this coulomb per mole of electrons. So because this one is the moles of electrons involved, okay, so it's cut. So what we get is the coulomb, the charge. So we just need to use the moles of iodines times the electrons involved, right, and times the Faraday constant. So we get this coulomb. Okay, so you need to use the Q equal to IT. So because now it's asking what is the average current used, so means it's going to be the I. So I equal to Q over T. Q already obtained. T must be in second. So because it's 8 minutes, so therefore it's 8 times 60. So eventually you get 0.429 ampere. If you want to make it fast, which I recommend you all to do these steps. It's actually better, step by step. If you want to make it fast, so you can use this one, Q equal to IT. So Q is equal to is actually NZF. So N is the moles that the produced, and Z is the electrons involved, and F is Faraday constant equal to IT. So I is of course is what we want to calculate, and T is the time, right? So eventually rearrange, you get the same value. Okay, part E. Ki is used as a source of iodide ion in the organic synthesis. So we have this example in figure 1.1. Okay, so from A to B, we know that from benzene to nitrobenzene, so it's undergo nitration. So the is reaction is electrophilic substitution, the mechanism, and from B to C is a reduction from this nitrate to this NH2. This is phenylamine. This amine means it's undergo reduction. Remove 2 oxygen, add 2 hydrogen. From C to D, okay, from the phenylamine to this benzene diazonium ion. You see that here, N2 positive. This benzene diazonium ion, which need to use the sodium nitrite and the acid. Okay, after that, these iodides that we mentioned just now will be the nucleophile substitutes the N2 positive there. Means eventually here this one, the N2 positive here, it will form the nitrogen, and it will form this iodobenzene. So this is the what I call the reactions, the steps involved in this part E. Okay, let's see what they want. Part 1, identify the reagents required for the step 1 and step 2. Reagents, step 1 is what? Step 1 is nitration. So we need to use nitration mixture because it's asking reagents only. So you just put concentrated this nitric acid and the concentrated H2SO4. Condition of course is 55 degrees C. The range is 50 to 60. Step 2 is a reduction. When it's a nitrobenzene reduced to the phenylamine, we must use the special reducing agent, which is this one. The tin, right, the SN, and the concentrated HCl. Better you put hot lah. Okay, hot tin and concentrated HCl. In the mark scheme, it's just tin and concentrated HCl. It should be followed by sodium hydroxide. Why? Because if under this condition concentrated this HCl, eventually it will form a salt. So it must be in alkaline conditions later. So it can form the amine, the phenylamine. So this is the standard answer according to the syllabus. Part 2. Step 3 occur in 2 stages. Step 3 again, let's see. Step 3. Okay, step 3 is from phenylamine to benzene diazonium ion. Okay, stage 1 is this sodium nitrite with HCl undergo acid-base reaction to produce HNO2. Very easy. So you just need to complete the equation. The sodium nitrite with HCl, okay, form the HNO2 and the salt NaCl. Basically, it's just NaCl and the HNO2 here, right? Okay, stage 2, the HNO2 reacts with C. C is this phenylamine to produce the benzene diazonium ion. Okay, this one no choice. You must remember how the equations to be. The phenylamine with the HNO3 and the acid. Okay, acid is the HCl, H plus. And with these three, it can form the benzene diazonium ion, C6H5. Okay, with this N2 positive. And remember, okay, plus 2 H2O. So this is the equations to form the benzene diazonium ion from the phenylamine. We must use this nitrous acid and the acid. In this case is HCl. Part 3, the iodide form. The iodide from Ki reacts with D in step 4. The mechanism shown in this 1.1 suggests the name of this mechanism. So suggest. Okay, because this iodide is nucleophile, obviously it substitutes the N2 here. So we can suggest it's a nucleophilic substitution. Okay, so answer very straightforward, nucleophilic substitution. Okay, that's all. Thank you.